Welcome to section 4.4, curve sketching techniques. Our goal today is to graph functions using the final version of the graphing strategy. So here's our graphing strategy. We've been adding to it a little bit every time. First, we analyze the function. We get the domain, the intercepts, and the asymptotes. Then we analyze the derivative, giving our partition numbers for the critical values, determining the intervals where it's increasing and decreasing, and then that will give us an idea of our local extrema. Then we analyze our second derivative, find the partition numbers, determine the intervals where it's concave up or concave down. That will tell us where the inflection points are, and putting all of this together, we'll be able to sketch a graph of our function. So, in problems 1 through 3, summarize the pertinent information obtained by applying the graphing strategy and sketch the graph. Our function f of x is x minus 4 over x plus 4. So, for step 1, we will analyze the function. So, what is our domain? Well, right now the only limitation we have is that x cannot equal 4. So our domain, our x-intercept will be when our numerator is equal to 0. So let's find our x-intercept. If x minus 4 is equal to 0, that means that x equal 4. Therefore, x-intercept is 4, 0. And at 0, we'll have 0 minus 4 over 0 plus 4. So negative 1. So our y-intercept will be 0, negative 1. Oh, this is not positive 4, this is negative 4, I'm sorry. We want the domain everywhere except where our denominator is 0. That was a negative 4. Okay, that makes more sense. So we've got domain is anything except negative 4. Our x-intercept is 4, 0. Our y-intercept is 0, negative 1. And the vertical asymptote is just our point of discontinuity. So I'm going to also label this our vertical asymptote. Horizontal, we'll find, that's when we take the limit as it goes to infinity. And here, since our exponents are the same, right, we have x to the 1 over x to the 1, then that tells us we'll take the coefficients. So it's just a 1, so vertical asymptote was negative 4, horizontal is just y equals 1. So we found all that we can find from our first derivative. Step 2. We'll look at our first derivative. And so f of x is x minus 4 over x plus 4. So f prime will take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared this is going to reduce to 8 over x plus 4 squared. And the only partition number here is the value that makes the denominator 0, or -4. So if our partition number is -4, then we can test -5 and -3, surrounding it, and see where is it increasing and where is it decreasing. So if we plug in -5, we'll get 8 over -5 plus 4, so -1 squared. That will just give us 8. So positive on this side. Over here, if we have f prime of -3, 8 over -3 plus -4, so 8 over 1 squared will give us 8. Positive on this side. So the function is increasing everywhere except at -4. From -infinity to -4, and then from -4 to positive infinity. Okay. Next, we'll look at our second derivative. And so we have 8 times x plus 4 to the -2. So we'll use our power rule. 8 times -2 will give us -16 x plus 4 minus 1, so to the -3. And then chain rule times 1. So I can rewrite this as -16 over x plus 4 cubed. And this tells us there's only one partition number, and it's still at -4. So we'll check again -5 and -3. So our second derivative at -5 will tell us concavity. So we have -16 over -5 plus 4. So -16 over -1 cubed. Negative over a negative will give us a positive. And then our second derivative at -3, -16 over -3 plus 4. So -16 over 1 cubed. Negative over a positive will give us a negative. So this is concave up, concave down. And -4 will be an inflection point. Now we sketch. Let's see, we'll have to sketch it over here. So we have our intercept for 0, y-intercept 0, -1, it's increasing until -4, and then decreasing, or increasing at -4. We have an inflection point. It goes from concave up to concave down. So -4 I'm just going to mark our vertical asymptote, horizontal asymptote, then we've got something like increasing and concave up, increasing and concave down, something like that. I could probably make this side better. Okay. And basically we're putting all of our information together to create our graphs. Okay. Negative 4x over x minus 3. So, step 1. First, we'll look at domain. We'll have, the only restriction is x equals 3. So, x cannot be, I keep doing that. X cannot be 3. That'll make our denominator 0. X-intercept, we'll have negative 4x equals 0, x equals 0, so we'll have 0, 0. Y-intercept, it's going to be negative 4 times 0 over 0 minus 3 equals 0, so also 0, 0. And our asymptotes, so vertical asymptote is, where's our discontinuity? That's at x equals 3. Horizontal asymptote, we'll look at the limit as it goes to infinity. Our exponent in the numerator, same as the denominator again. So we'll take the coefficient, negative 4 over 1. So we'll have y equal negative 4. Okay, step 2. Let's see how much space we have. Okay. So our derivative, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that will give us 12 over x minus 3 squared. This gives us our partition number of 3. So if we're looking around 3, we can test 2 and 4. So our derivative at 2, 12 over 2 minus 3 squared, so 12 over 1 is 12. And 4 will give us 12 over 4 minus 3, so squared, so 12 over 1 is 12. So it's increasing and increasing. Our second derivative So we have the bottom times the derivative of the top minus the top times the derivative of the bottom. And the bottom squared. Okay, so this will simplify. Negative 24. And if we have an x minus 3 over an x minus 3, then we'll have x minus 3 cubed left. Okay, so now we have a partition number still at 3. So again, we'll check 2 and 4. Our second derivative at 2 will give us negative 24 over 2 minus 3 cubed. So negative 24 over negative 1 is positive. And then our second derivative at 4, negative 24 over 4 minus 3 cubed, negative 24 over 1, negative 24. Okay. So we have concave up, concave down. And remember, 3 is undefined, f of 3 is undefined, so we don't have our inflection point there. That's our asymptote. So we'll take all of this and sketch. Zero, zero. Vertical asymptote at 3. And horizontal at negative 4. We are increasing concave up and then concave down. Okay, so we're increasing, we hit that point. Make sure we're concave up, this part's concave down, something like that. I'll probably make that part better. Okay. So basically we're just outlining everything algebraically and then using it to make our graph. Okay, domain e to the negative 3x squared, so we have no restrictions, it's all real numbers. Our x-intercept, what makes it 0? None. Our y-intercept, so f of 0, e to the negative 3 times 0 squared. That's going to give us 1, so 0, 1. Vertical asymptote, since our domain's all real numbers, we have no vertical asymptote. Horizontal asymptote, if we take the limit of it, the function as it goes to infinity, so as this function goes to infinity, our horizontal asymptote gets closer and closer to 0, right? We plug in bigger and bigger numbers, it gets closer and closer to 0. Okay, so next step, our first derivative we'll take the derivative, so we've got negative 6x e to the negative 3x squared. So our partition number is just 0. So we'll do -1 and +1. Our derivative at -1 will give us -6 times -1 e to the -3 times -1 squared. So that's about 0.299, so positive. And our derivative at 1, -6 times 1 e to the -3 times 1 squared, that will give me -0.299, so negative. So we're increasing and then we're decreasing. That tells us we have a max at 0. Now we'll look at our second derivative. Taking the derivative again, we'll have -6x, -6x e to the -3x squared plus e to the -3x squared times -6. So if we simplify that, we'll have 6e to the -3x squared times 6x squared minus 1. So we're factoring that out. Now this one gives us two partition numbers, right? Where we set it equal to 0. And when we set it equal to 0, we'll have negative 0.41 and positive 0.41. So let's test -1, 0, and +1, just to keep it easy on ourselves. Our second derivative at -1 will give us 6e to the -3 times -1 squared times 6, -1 squared minus 1. So that gives us 1.49 positive. Concave up. At 0, we'll have 6e to the -3 times 0 squared times 6 times 0 squared minus 1. So we'll be left with -6. Concave down. Our second derivative at 1, 6e -3 times 1 squared times 6 times 1 squared minus 1. So positive 1.49. So concave up. This is telling us we have inflection points. And now we can take all of this and sketch. horizontal asymptote, y equals 0. Zero, 1 is our y-intercept. Maybe I'll move that up. Then we are increasing to 0 and decreasing. And then we're also going concave up, concave down, concave up. So it's gonna go something like increasing, concave up, concave down, concave up. Something like that. Okay, so again, to summarize, we're algebraically calculating all these things, and then we piece them together to create our graph. You want to do these without your graphing calculator, but you can check your graph after on the graphing calculator. That way you can make sure that you've done everything correctly, you sketched it properly.